Hi there, welcome to Ancient Cosmos Sleep. Tonight we lift our eyes into a darkness scattered with tiny points of light and wonder whether those distant glimmers are merely stars, or whether each one hides entire cities of suns beyond imagination. You stand beneath a clear night sky, the air cool and still, and the universe stretches above you like an endless black ocean dusted with silver. Somewhere out there are galaxies so large that their light takes hundreds of thousands of years to cross them, and yet from where you stand, they appear no larger than a grain of dust balanced on the tip of a pin. The funny thing is that asking how many galaxies exist in the universe sounds simple at first. It feels like the sort of question that should have a neat answer tucked inside a textbook somewhere. But the universe, as usual, refuses to cooperate. It behaves like a cosmic magician who keeps pulling larger hats out of even larger hats. And here's a cheerful reality check. If you attempted to visit every galaxy one by one, you probably would not survive the itinerary. Even at impossible speeds, the schedule would be somewhat inconvenient. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, feel free to post your location and local time. It's always fascinating to see where in the world people are listening from as we all drift together beneath the same universe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You continue gazing upward. The first thing you notice is that your eyes naturally try to simplify what they see. Human beings are experts at turning complexity into manageable stories. We look at a cloud and see an animal. We look at random stars and imagine a hunter, a bear, or a giant scorpion. When you stare into the night sky, your brain quietly suggests that everything visible belongs to one enormous collection, one sky, one universe, one neighborhood. Yet hidden behind that simple view lies an astonishing truth. The stars you can see with your naked eye belong almost entirely to a single galaxy, the Milky Way. That glowing band stretching across dark skies is not a cloud. It is the combined light of countless stars packed together in a vast spiral system. Today, this seems obvious, but for much of human history, nobody knew exactly what the Milky Way was. A mainstream historical fact worth remembering is that the ancient Greek philosopher Democritus suggested that the Milky Way might be composed of countless distant stars. It was a remarkably insightful idea, especially considering he lacked a telescope and had to rely entirely on observation and reasoning. Not everyone agreed, of course. Human history is filled with intelligent people confidently explaining things that later turned out to be spectacularly incorrect. This tradition remains alive and well. As centuries passed, observers proposed all sorts of explanations. Some imagined heavenly vapor. Others pictured celestial fires. The Milky Way became a cosmic mystery stretching across generations. Then telescopes arrived. When early astronomers pointed these new instruments skyward, the universe began revealing details it had previously kept hidden. More stars appeared, then more. Then so many more that counting them seemed hopeless. And this introduces the central challenge of tonight's question. Before you can count galaxies, you must know what a galaxy actually is. That sounds straightforward, but nature enjoys blurry boundaries. A galaxy is generally understood as a huge collection of stars, gas, dust, and dark matter bound together by gravity. Yet galaxies come in many forms. Some contain trillions of stars, others possess only a few million. Some are elegant spirals, others resemble glowing blobs. A few appear as though they were assembled by an exhausted cosmic intern working through a holiday weekend. Even defining where one galaxy ends and another begins can become surprisingly tricky. You drift deeper into the idea. Imagine standing on a beach at night and trying to count distant islands. Large islands are easy. Tiny islands become harder. islands hidden by fog become nearly impossible. Some might be so faint that you never realize they are there at all. The universe presents exactly this problem. Galaxies are the islands, space is the ocean, and the fog is distance itself. The farther away a galaxy is, the fainter it appears. Eventually, even the most powerful telescopes struggle to detect it. This means that every count of galaxies comes with uncertainty. Astronomers do not simply open a cosmic directory and read the final number. Instead, they estimate, compare observations, build models, and constantly revise their conclusions as better data arrives. Historians still argue whether certain ancient observations truly recognized the nature of the Milky Way or merely described its appearance. In a similar way, astronomers today continue debating details of galaxy formation and population estimates. The story remains unfinished. There is also a wonderfully quirky tidbit hidden in this tale. Some cultures described the Milky Way as a celestial river. Others imagined it as a road for souls, a pathway for gods, or even spilled heavenly milk crossing the sky. Long before scientific measurements existed, human imagination was already trying to make sense of the glowing band overhead. And perhaps that instinct remains unchanged. You sit beneath the same sky as countless generations before you. The tools have improved dramatically, but the feeling is familiar. Curiosity still pulls at you. How many galaxies are out there? A few thousand? A few million? A few billion? The answer, as you will gradually discover, becomes larger every time humanity builds a better way to look. For now, you simply rest beneath the darkness and allow the scale of the question to settle into your thoughts. Somewhere beyond the stars visible tonight are galaxies whose light began traveling long before humans built cities, cultivated crops, or even imagined asking questions about the universe. And somewhere among those countless distant systems lies the beginning of one of astronomy's greatest adventures, learning that the cosmos is far larger than anyone once believed. You remain beneath that immense sky, carrying with you the realization that before counting galaxies, you must first understand the one galaxy you already inhabit. And that turns out to be a surprisingly difficult assignment. After all, imagine trying to draw a complete map of a forest while standing deep among the trees. Every direction contains trunks, branches, shadows, and confusing perspectives. You can walk around, you can make measurements. But seeing the whole structure at once is nearly impossible. That is your situation inside the Milky Way. You are not looking at your galaxy from the outside. You are embedded within it, riding around the center at extraordinary speed while barely noticing the motion. Every second, you travel through space along with Earth, the solar system, and billions of neighboring stars. Yet your morning coffee remains reassuringly in its cup. The Milky Way itself is enormous. Current estimates suggest it contains hundreds of billions of stars. Some studies lean lower, others higher, and astronomers continue refining the number as better observations become available. If you attempted to count one star every second without taking breaks, sleeping, eating, or questioning your life choices, you would still need thousands of years to finish. 3 seconds in, you would already regret volunteering. The galaxy stretches across roughly 100,000 light-years or more. A light-year, remember, is the distance light travels in a year. Since light moves at about 300,000 kilometers per second, a single light-year represents a distance so vast that ordinary human intuition immediately files a complaint. Your own star, the Sun, lives in one of the Milky Way's spiral arms, comfortably removed from the crowded central regions. This is fortunate. The galactic center is a far busier neighborhood. Stars crowd together in greater numbers, and at the heart of it all lurks a supermassive black hole known as Sagittarius A. Despite sounding like the final boss of an astronomy video game, Sagittarius A mostly sits quietly in the center. influencing its surroundings through gravity, a mainstream historical fact enters the story here. In the early 17th century, Galileo Galilei pointed a telescope toward the Milky Way and discovered that the hazy band consisted of countless individual stars. This observation transformed humanity's understanding of the heavens. Suddenly, the Milky Way was not celestial fog, it was structure, it was population, it was architecture, and perhaps most importantly, it suggested that the universe might be far more complex than anyone had imagined. Yet, even after Galileo's discovery, people still assumed the Milky Way might represent nearly everything that existed. You can understand why. The galaxy already seemed unimaginably large. If you could somehow shrink the Milky Way to the size of North America, the solar system would become smaller than a coin. Earth itself would be practically invisible. Humans have a talent for feeling important until astronomy arrives and politely disagrees. As astronomers mapped stars throughout the 18th and 19th centuries, they began noticing patterns. The Milky Way appeared flattened rather than spherical. Star density varied depending on where observers looked. Some regions glowed more brightly than others. Slowly, a rough picture emerged. Yet the picture contained serious flaws. Dust clouds threaded through the galaxy like cosmic curtains, blocking visibility. Observers often mistook these dark regions for empty space. In reality, stars lurked behind them, hidden from view. Imagine trying to estimate the size of a city while thick fog conceals entire neighborhoods. That was the challenge. The Milky Way kept secrets. Some of those secrets generated remarkably creative explanations. A quirky historical tidbit comes from the 19th century, when various observers proposed elaborate structures and shapes for the galaxy based on incomplete information. Some models looked more like abstract artwork than scientific diagrams. In fairness, they were attempting to reconstruct a colossal structure while trapped inside it. That is roughly equivalent to determining the shape of an entire elephant while standing on one of its toenails. As observations improved, astronomers gradually recognized that the Milky Way was just one stellar system among many possibilities, but they still lacked proof. The biggest mystery involved strange fuzzy objects visible through telescopes. These objects became known as nebulae. Some appeared cloud-like, others displayed beautiful spiral patterns. The question was simple enough to ask and incredibly difficult to answer. Were these nebulae nearby objects inside the Milky Way? Or were they entirely separate systems located at unimaginable distances? Nobody knew. Historians still argue whether certain astronomers of the era appreciated just how revolutionary the answer would become. Some hints appeared in letters and notes, but certainty remains elusive. Meanwhile, the debate quietly intensified. You could almost feel the tension building. Every new observation added another clue. Every improved telescope revealed additional details. Every estimate raised fresh questions. And throughout all of this, humanity continued occupying a curious position. You lived inside a galaxy while trying to determine whether other galaxies even existed. It was a bit like discovering your village and wondering whether neighboring continents might be hidden beyond the horizon. The more carefully astronomers examined the Milky Way, the more they realized that understanding one galaxy might unlock the nature of many others. Ports emerged, stars formed clusters, gas clouds densened into new suns. Gravity shaped enormous structures over millions and billions of years. The galaxy behaved less like a random collection of lights and more like a living ecosystem operating on cosmic timescales. As you drift deeper into this realization, the Milky Way begins to feel simultaneously larger and smaller, larger because its true scale defies comprehension. Smaller because evidence is quietly accumulating that it may not be unique, somewhere beyond the visible stars, Beyond the dusty spiral arms, beyond the limits of 19th century telescopes, answers wait in the darkness. The universe is preparing to reveal that the Milky Way is not the whole story, it is only the first page, and soon a fierce scientific argument will erupt over those mysterious spiral nebulae. An argument that will transform humanity's picture of reality forever. The Milky Way continues to fill your imagination as you move forward through the 19th century, a period when astronomers possess increasingly powerful telescopes but still lack crucial pieces of the cosmic puzzle. You might assume that better instruments automatically produce better answers. They do, eventually, but first they often produce better questions. As observers scan the heavens, they catalogue thousands of strange objects. Some appear as clusters of stars, others resemble glowing clouds. A particularly puzzling group displays elegant spiral shapes. These become known as spiral nebulae. At first glance, they look beautiful. At second glance, they look confusing. At third glance, they become the source of one of astronomy's greatest mysteries. The problem is distance. If astronomers know how far away these spirals are, they can determine what they truly are. If the spirals lie nearby, then they are probably structures within the Milky Way. If they are extremely distant, they could be entire stellar systems comparable to the Milky Way itself. Unfortunately, measuring those distances proves extraordinarily difficult. You are living in an era before modern detectors, before space telescopes, before digital imaging, and before many of the techniques astronomers now take for granted. Much of astronomy still depends on patient observation, careful sketching, and endless nights spent peering through eyepieces. A mainstream historical fact from this period involves the tireless work of astronomers cataloguing nebulae. In the late 18th century, French astronomer Charles Messier compiled a famous list of fuzzy objects, so that comet hunters would not mistake them for comets. His catalogue included many nebulae and galaxies, although nobody realized at the time that some entries were entire galaxies far beyond the Milky Way. Imagine accidentally placing another galaxy on a checklist labeled "Things that are not comets." History occasionally enjoys a good understatement. As the 19th century progresses, telescopes improve dramatically. Spiral structures become easier to see. Observers sketch magnificent whirling forms scattered across the sky, yet the mystery deepens. Some astronomers believe the spirals are relatively small objects located within our galaxy. Others suspect they are vast island universes floating independently through space. The phrase "island universe" becomes increasingly popular. It carries a poetic image. Each galaxy would be a lonely continent of stars surrounded by an ocean of darkness. A quirky tidbit from the era involves enthusiastic attempts to classify nebulae based solely on appearance. Astronomers sometimes organized them into categories that later turned out to have little connection to their actual nature. Nature, as usual, had not bothered to read the classification handbook. The universe has a habit of ignoring filing systems. While debates continue, another challenge emerges. The Milky Way itself is not fully understood. Astronomers still disagree about its size. Some estimates place the Sun near the center. Others place it elsewhere. Large clouds of dust continue hiding significant portions of the galaxy, leading observers to draw conclusions based on incomplete information. It is like trying to assemble a giant jigsaw puzzle while several hundred pieces remain under the couch. You can feel scientific uncertainty everywhere, and uncertainty is not a weakness. In science, uncertainty is often a sign that discovery is approaching. The most exciting moments occur when existing explanations stop fitting the evidence. As more spiral nebulae are observed, astronomers begin noticing something remarkable. There are a lot of them. Not a handful, not dozens, thousands. Every direction seems to reveal more. This abundance raises uncomfortable questions. If these objects all belong to the Milky Way, why are they distributed in such curious ways? Why do some appear brighter? Why do some display distinct structures? Why do they look so much like miniature galaxies? No answer satisfies everyone. Historians still argue whether certain researchers privately accepted the island universe idea before publicly supporting it. Letters, notebooks, and personal correspondence sometimes suggest greater uncertainty than official publications reveal. Scientific revolutions rarely arrive in neat packages. Most emerge through hesitation, disagreement, and gradual shifts in thinking. As you drift through observatories lit by lanterns and early electric lights, you encounter generations of astronomers working patiently beneath cold night skies. Many spend entire careers studying faint smudges of light. Some never live long enough to learn what those smudges truly are, yet their measurements matter. Each observation becomes another stepping stone. Each sketch contributes another clue. Each debate sharpens the questions, and the questions themselves are becoming increasingly profound. If the spiral nebulae are separate galaxies, then the universe is vastly larger than imagined. If they are not, then the Milky Way remains the dominant structure in existence. The difference between these possibilities is difficult to overstate. One vision places humanity inside a galaxy that effectively defines the universe. The other places humanity inside a galaxy that is merely one among countless others. Your place in reality hangs on the answer. There is also a subtle emotional shift occurring. For thousands of years, people have gradually moved away from the center of things. Earth is not the center of the solar system. The sun is not the center of the universe. And now the Milky Way itself may not be the center of everything. The universe keeps expanding around human expectations, not physically expanding yet, that revelation is still ahead, but expanding conceptually. Every generation discovers that reality is larger than it previously believed. Some find this unsettling. Others find it exhilarating. You can almost sense astronomy standing on the edge of a cliff, peering into a fog-filled valley below. The landscape is hidden, the destination remains uncertain, but the outlines of something enormous are beginning to emerge. Soon, astronomers will stop merely speculating about spiral nebulae and start confronting the question directly. The argument will become famous, careers will be built upon it. Reputations will rise and fall with it, and the answer will permanently alter humanity's understanding of the cosmos. For now, though, the spiral nebulae continue shining quietly in the darkness, withholding their secret just a little longer, waiting for the moment when technology and determination finally become powerful enough to uncover the truth. The mystery of the spiral nebulae now grows impossible to ignore. You have traveled through decades of observations, sketches, arguments, and increasingly sophisticated telescopes. The evidence has accumulated like snowflakes in a winter storm. Each individual piece seems small. Together, they begin to reshape the landscape. By the early 20th century, astronomy finds itself facing a fundamental question. How big is the universe? Not in the modern sense of measuring billions of light years. At this stage, astronomers are still trying to determine whether the Milky Way encompasses nearly everything that exists, or whether it is merely one member of a much larger population. The debate becomes so important that it earns a famous place in scientific history. A mainstream historical fact emerges in 1920 with what later becomes known as the Great Debate, a public discussion between Harlow Shapley and Heber Curtis. Both men are highly respected, both are intelligent, both have evidence, and both disagree. Shapley argues that the Milky Way is enormous and contains the spiral nebulae within it. Curtis argues that many spiral nebulae are separate galaxies, independent of the Milky Way. You can imagine the atmosphere. not a shouting match, not dramatic television panels with flashing graphics. Just careful scientific disagreement carried out through observations, calculations, and competing interpretations, though admittedly with enough professional stubbornness to power a small city. Shapley possesses strong reasons for his position. His studies suggest the Milky Way is much larger than many earlier estimates. He correctly argues that the Sun does not occupy the galactic center. Instead, humanity resides off to one side. This alone represents a major shift in perspective. Meanwhile, Curtis examines the spiral nebulae and notices characteristics suggesting enormous distances. Some display dark lanes and structures that seem difficult to explain if they are merely local objects. The evidence points in different directions, and nature refuses to reveal the answer immediately. Historians still argue whether either participant truly won the great debate. The reality is more complicated. Both astronomers proved correct about certain things and mistaken about others. Science often works that way. Progress does not always arrive through a single hero defeating a villain. More often, multiple researchers contribute pieces of a puzzle that only later generations fully assemble. As you listen to the arguments, the scale of the issue becomes breathtaking. Suppose Curtis is correct. Suppose those spiral nebulae are actually galaxies, then each faint swirl contains billions of stars. Each one could possess planets. Each one might contain structures as vast and complex as the Milky Way. Suddenly, the universe becomes staggeringly larger. A quirky tidbit from this era involves how some popular publications portrayed astronomical discoveries. Newspapers occasionally exaggerated findings or simplified debates to make them more accessible. Readers could encounter descriptions of cosmic questions that sounded almost like detective mysteries. To be fair, they were detective mysteries. The suspects simply happened to be galaxies. Meanwhile, astronomers continue gathering data. Photographic technology improves. Telescopes become more capable. Observatories spend night after night collecting information from distant objects. The spiral nebulae remain frustratingly elusive. They appear bright enough to observe, but too distant to measure easily. Think of standing on a shoreline at dusk and trying to estimate the distance to a lantern on a far-off island. The light is visible. The island is visible. Yet determining its exact location proves remarkably difficult. That challenge now confronts astronomy. The universe has become a giant geometry problem. Fortunately, astronomers enjoy geometry, at least most of the time. One of the most important developments comes from the study of variable stars. Certain stars brighten and dim in predictable ways. By measuring these changes, astronomers can estimate distances. These stars function like cosmic measuring tapes, not perfect measuring tapes. More like measuring tapes stretched across absurdly large portions of reality. Still, they work. Researchers begin searching for such stars within the spiral nebulae. If they can identify them, they might finally determine the true distances involved. The stakes are enormous. A successful measurement could settle the debate. It could reveal whether the Milky Way represents the universe or merely a single neighborhood within it. As the years pass, anticipation builds. You can almost feel astronomy holding its breath. Every new observation carries possibility. Every photographic plate might contain the clue everyone seeks. At the same time, broader questions emerge. Why do galaxies have spiral shapes? How do stars form? What governs the structure of the cosmos? Even before the galaxy question is resolved, astronomers are beginning to glimpse deeper mysteries waiting beyond it, and wonders generate questions. Questions generate discoveries. Discoveries generate even larger questions. The cycle continues. The great debate becomes memorable not because it ends everything, but because it marks a turning point. It forces astronomers to confront assumptions that had guided thinking for generations. Perhaps the Milky Way is not unique. Perhaps the universe contains countless stellar systems. Perhaps humanity occupies an even smaller corner of reality than previously imagined. Such ideas are difficult to absorb. Human intuition evolved for forests, rivers, mountains, and weather. It did not evolve for hundreds of billions of stars. It certainly did not evolve for hundreds of billions of galaxies. Yet the evidence keeps pushing in that direction. The spiral nebulae remain suspended in the darkness, beautiful and mysterious. They seem almost aware of the confusion surrounding them. Of course they are not, but it is easy to imagine them quietly waiting for humanity to catch up, and catch up it soon will. Because a young astronomer working with one of the most powerful telescopes on Earth is about to make observations that transform the debate into a historical milestone. The universe is preparing to reveal that the spiral nebulae are far more distant and far more significant than many had dared to believe. The fog surrounding the cosmic shoreline is beginning to lift, and beyond it, entire galaxies are waiting to come into view. The fog finally begins to clear, not all at once, of course. The universe rarely delivers its secrets with dramatic music and perfect timing. Instead, it offers clues, measurements, and observations that slowly converge into a new picture of reality. You now find yourself in the 1920s, standing at one of the great turning points in the history of astronomy. High above the valleys of California sits the famous Mount Wilson Observatory, home to the 100-inch Hooker telescope, the most powerful telescope in the world at the time. To astronomers, this instrument is something close to magic. It allows them to see farther and more clearly than ever before. And one astronomer in particular is about to use it to change humanity's understanding of the cosmos. His name is Edwin Hubble. A mainstream historical fact unfolds in 1923 when Hubble identifies Cepheid variable stars within the spiral nebula known today as the Andromeda Galaxy. This may sound like a small technical achievement. It is not. It is one of the most important observations in the history of science. Remember those variable stars discussed earlier. Their brightness changes in predictable ways, allowing astronomers to estimate their true luminosity and therefore their distance. Hubble measures these stars in Andromeda. The result is astonishing. Andromeda is far too distant to belong to the Milky Way. Far beyond, it must be an entirely separate galaxy. The great debate is effectively settled. The spiral nebulae are not nearby clouds. They are galaxies, entire galaxies, each one a colossal collection of stars existing independently in space. You can almost feel the universe suddenly expanding around you. Yesterday, the Milky Way appeared to be nearly everything. Today, it becomes one galaxy among many. The psychological impact is difficult to overstate. Imagine spending your entire life believing you live on the only continent in existence, only to discover that vast oceans contain countless additional continents stretching beyond every horizon. That is roughly the scale of the revelation. Humanity's cosmic address instantly becomes less central and far more interesting. The universe grows enormously, and this is only the beginning. Because Hubble's work soon leads to another extraordinary discovery. As astronomers study distant galaxies, they notice something peculiar. Most galaxies appear to be moving away from us. Not because Earth occupies a special position, not because the Milky Way is pushing them outward. Rather, space itself appears to be expanding. The farther away a galaxy is, the faster it tends to recede. This relationship becomes known as Hubble's law. You can visualize it by imagining raisins embedded within rising bread dough. As the dough expands, every raisin sees other raisins moving away. No raisin occupies the center. The expansion occurs everywhere at once. The analogy is imperfect, but it captures the basic idea, and it introduces one of the strangest concepts in modern science. The universe is not static. It evolves, it changes, it grows. A quirky tidbit from this era involves how difficult it was for some scientists to accept the idea of an expanding universe. The notion felt deeply counterintuitive. Even Albert Einstein initially preferred a static cosmos and famously adjusted his equations to accommodate that expectation. Reality, however, had other plans. The universe continued expanding regardless of anyone's preferences. Space does not generally hold committee meetings before making decisions. As observations improve, astronomers begin identifying galaxies everywhere they look: spiral galaxies, elliptical galaxies, irregular galaxies, large ones, small ones, bright ones, faint ones. The night sky transforms from a collection of isolated objects into a vast cosmic landscape populated by countless stellar systems. The scale becomes almost overwhelming. The Milky Way contains hundreds of billions of stars. Now imagine hundreds of billions of galaxies. And remember, astronomers have not yet reached that estimate. At this stage, they are only beginning to understand the population. Still, the direction is clear. The universe is vastly larger than previous generations imagined. Historians still argue whether the cultural significance of these discoveries was immediately appreciated by the public. Scientific communities quickly recognized the importance, but broader society absorbed the implications more gradually. That is understandable. The human brain evolved to track fruit trees and weather patterns. Processing billions of galaxies requires a bit more effort. As you continue drifting through the decades, observatories around the world begin refining galaxy catalogs. Researchers classify shapes, measure distances, estimate brightness, MAM distributions. Every observation contributes another piece to an emerging cosmic census, yet significant limitations remain. Telescopes can only see so far. Distant galaxies appear faint. Some vanish entirely into observational darkness. Astronomers know they are probably missing large numbers of galaxies. The challenge shifts from proving galaxies exist to determining how many there are. And that question proves surprisingly difficult. Suppose you look at a tiny patch of sky and count visible galaxies. Can you assume the rest of the sky contains similar numbers? Perhaps, but what if some regions differ? What if faint galaxies escape detection? What if entire populations remain hidden? The counting problem becomes increasingly complex. The more astronomers learn, the more they realize how incomplete their surveys remain. Yet that incompleteness is itself informative. If telescopes continue finding new galaxies whenever they look deeper, then the true total must be enormous, perhaps far larger than current estimates suggest. You settle into that thought. A century ago, astronomers debated whether galaxies existed at all. Now they are confronting a different challenge. There may be so many galaxies that counting them becomes one of the greatest measurement problems in science. The universe has expanded from a single stellar city into an immense archipelago of light, and humanity is only beginning to chart the map. Soon, increasingly powerful telescopes and ambitious sky surveys will attempt something extraordinary, a true census of the cosmos. For the first time, astronomers will try to estimate how many galaxies inhabit the observable universe, and the numbers they uncover will stretch imagination to its limits. The universe now feels much larger than it did only a few decades earlier. You have watched the Milky Way lose its status as the entire cosmos. You have seen distant spiral nebulae revealed as galaxies in their own right. You have witnessed the discovery that space itself is expanding, and yet the central question remains: how many galaxies are there? The answer cannot come from observing a handful of galaxies. It requires something far more ambitious. It requires a census, not the sort of census that involves forms, paperwork, and someone politely asking how many people live in your household. Galaxies are not especially cooperative with administrative procedures. Instead, astronomers must survey enormous regions of the sky, cataloging every detectable galaxy and then using those observations to estimate the larger population. This task becomes one of the great scientific projects of the 20th century. A mainstream historical fact appears as observatories begin producing large photographic sky surveys. Projects such as the famous Palomar Observatory Sky Survey systematically photograph vast portions of the heavens, creating detailed maps that astronomers use for decades. For the first time, researchers possess something approaching a comprehensive inventory of visible galaxies, not complete, not perfect, but revolutionary. Imagine trying to estimate the number of trees in a forest. You could count every tree individually, which might take a while and lead to several emotional breakdowns. Or you could sample representative areas and use mathematics to estimate the total. Astronomers adopt a similar strategy. They observe sections of the sky, count galaxies, measure brightness, estimate distances, then build statistical models. The process sounds straightforward. Reality, naturally, introduces complications. Some galaxies are bright and easy to spot. Others are faint, some are nearby, others lie so far away that their light arrives weakened after billions of years of travel. Many galaxies overlap visually when viewed from Earth, creating the cosmic equivalent of trying to count distant birds flying through fog. The deeper astronomers look, the more galaxies appear. This is both exciting and mildly annoying. Every time researchers think they are approaching a reliable count, improved instruments reveal additional objects. The universe keeps increasing the inventory. A quirky tidbit emerges from galaxy classification efforts during this era. Astronomers spend enormous amounts of time sorting galaxies by shape. Spirals, ellipticals, lenticulars, irregulars. The categories become increasingly detailed. Some galaxies fit neatly. Others seem determined to ignore organizational standards. It is as though the universe occasionally submits forms marked other just to keep things interesting. Meanwhile, observations reveal another fascinating truth. Galaxies are not distributed randomly. Gravity encourages them to gather. They form groups, clusters, superclusters, enormous structures spanning hundreds of millions of light years. You begin to realize that counting galaxies is not simply about tallying isolated objects. It is about understanding a vast cosmic web. Galaxies influence one another. They collide mi-exteng material. Sometimes entire galaxies pass through one another like ghostly cities made of stars. Contrary to what science fiction movies often suggest, individual stars rarely crash together during these encounters because the distances between stars are immense. Space is surprisingly empty. A galaxy can contain hundreds of billions of stars and still consist mostly of nothing. That sentence alone feels like astronomy showing off. Historians still argue whether early models adequately captured the large-scale structure of the universe, or whether observational biases distorted initial conclusions. As better surveys arrive, many earlier assumptions require adjustment. Science continues refining its map. By the middle of the 20th century, astronomers estimate that the observable universe contains billions of galaxies. Billions, already an astonishing number. If every galaxy were represented by a grain of sand, you would possess enough sand to fill enormous landscapes. Yet researchers remain cautious. They know observational limitations persist. Many galaxies remain invisible to existing instruments. Distance hides them, faintness hides them, cosmic dust occasionally hides them. The universe seems determined to play an endless game of hide and seek. And the universe is very good at hiding. You drift through decades of technological progress. Larger telescopes rise atop mountains. Electronic detectors replace photographic plates. Computers begin assisting with analysis. Data accumulates at unprecedented rates. Each advancement improves humanity's ability to conduct a galactic census. The numbers become increasingly sophisticated. Astronomers no longer merely ask whether galaxies exist. They investigate populations, distributions, masses, chemical compositions, and evolutionary histories. Entire fields of research emerge around these questions. Yet despite all this progress, an uncomfortable realization persists. Most galaxy estimates depend on what telescopes can actually see. What about galaxies too faint to detect? What about galaxies so distant that their light barely reaches us? Could vast populations remain hidden? The possibility hangs over every calculation. You can imagine standing on a shoreline at night, counting visible ships on the horizon. The count is accurate as far as it goes. But darkness conceals additional vessels beyond sight. The challenge is determining how many. Astronomers confront exactly this problem on a cosmic scale. The visible sample is only part of the story. The unseen population may be much larger. As the 20th century progresses, increasingly sensitive observations begin hinting at the answer. Every improvement reveals additional galaxies. Every deeper survey increases the count. Every advance suggests that the universe contains far more islands of light than anyone previously suspected. And somewhere ahead lies a telescope that will transform the question entirely. A telescope that will stare into seemingly empty patches of sky and discover that they are anything but empty. When that happens, humanity's estimate of the galactic population will undergo another dramatic revision. The cosmic census is about to become far more ambitious, and the universe is about to reveal that even billions of galaxies may represent only the beginning of the story. The galaxy census continues to grow, but a persistent question remains in the back of every astronomer's mind. How many galaxies are we missing? You can only count what you can see, and throughout the 20th century, researchers repeatedly discover that the universe contains more than previously visible. Every new generation of telescopes pushes farther into space and uncovers additional galaxies lurking beyond earlier limits. The pattern becomes almost predictable. Build a better telescope. Find more galaxies, repeat. Then comes one of the most important observational tools ever created, the Hubble Space Telescope, launched above Earth's atmosphere in 1990. Hubble gains a clear view of the cosmos without atmospheric distortion. After early technical difficulties are corrected, it begins producing images that transform astronomy. A mainstream historical fact arrives in the mid-1990s when astronomers decide to attempt an unusual experiment. Instead of pointing Hubble at a bright galaxy or a famous nebula, they aim it at a tiny patch of sky that appears nearly empty. Not mostly empty, almost completely empty. Many scientists wonder whether the effort is worthwhile. Why spend valuable telescope time looking at what seems to be nothing? The answer turns out to be extraordinary. After exposing the camera for days and combining the observations, astronomers create what becomes known as the Hubble Deep Field. The image is stunning. The supposedly empty region is packed with galaxies, thousands of them, tiny spirals, distorted smudges, ancient galaxies whose light has traveled for billions of years before reaching the telescope. What appeared empty was actually overflowing with cosmic structure. You can imagine the reaction. It is like examining a grain of sand on a beach and discovering it contains thousands of hidden cities. Suddenly, every dark patch of sky becomes suspicious. Maybe it is not empty at all. Maybe it simply requires deeper observation. The deep field changes how astronomers think about galaxy populations. Instead of counting only the obvious galaxies, researchers begin estimating how many exist beyond ordinary detection limits. And the answer grows rapidly. A quirky tidbit from the Hubble era is that some of the galaxies visible in deep field images are so faint that they appear as only a handful of pixels. Entire collections of billions of stars can occupy a space smaller than a punctuation mark on your screen. Somewhere out there, a galaxy containing countless suns is effectively represented by what looks like cosmic lint. Scale becomes increasingly difficult to grasp. The Hubble Deep Field is followed by additional projects. The Hubble Ultra Deep Field, the Extreme Deep Field, longer exposures, better cameras, more distant targets. Each image reveals additional galaxies, each pushes farther back in time. Because looking farther into space also means looking farther into the past. Light requires time to travel. When you observe a galaxy 1 billion light-years away, you see it as it existed 1 billion years ago. When you observe a galaxy 10 billion light-years away, you see a much younger universe. Astronomy becomes a form of time travel, conveniently one way, admittedly, yet still impressive. Historians still argue whether certain early interpretations of deep field observations underestimated the complexity of galaxy evolution. As new data arrives, astronomers repeatedly revise models describing how galaxies form and change across cosmic history. The deeper humanity looks, the more complicated the story becomes. And complexity is exactly what the deep fields reveal. Some galaxies appear mature, others seem chaotic. Collisions and mergers are common, discharges vary dramatically. The early universe looks far less orderly than the modern one. You begin to understand why counting galaxies is difficult. Galaxies are not static objects sitting quietly on shelves, waiting to be inventoried. They evolve, they merge, they grow, they transform. Some disappear into larger galaxies, others form from smaller building blocks. The population changes over time. That means astronomers must answer multiple questions simultaneously. How many galaxies exist now? How many existed in the past? How many are too faint to detect? How many have merged into larger systems? The cosmic census becomes a moving target. Still, the deep field observations provide an astonishing clue. If a tiny patch of sky contains thousands of galaxies, then the entire sky must contain enormous numbers. Researchers begin extrapolating. They count galaxies in sampled regions, calculate average densities, estimate totals across the observable universe. The resulting figures are breathtaking. For years, a common estimate settles around 100 billion galaxies. 100 billion, even saying the number feels excessive. Imagine attempting to visit one galaxy per second. You would still require thousands of years just to name them all, and that estimate itself may be incomplete. As astronomers continue analyzing deep field data, some researchers suspect vast populations of faint galaxies remain undetected. The visible universe may contain significantly more galaxies than earlier counts suggest. The implications are profound. If additional galaxies exist below current detection thresholds, then humanity's cosmic census could be missing most of the population. The universe may resemble an iceberg. The Vidial galaxies form the portion above water. Hidden galaxies comprise the much larger structure below. You settle into that possibility. For generations, astronomers expanded the universe from one galaxy to many galaxies. Now they are beginning to suspect that even their revised estimates fall short. The deep fields have opened a new window. Through it, the cosmos appears richer, denser, and more crowded than ever imagined. And soon, careful analysis of those observations will lead to one of the most dramatic revisions in the history of galaxy counting. The total may not be hundreds of billions, it may be something far larger. The universe, once again, is preparing to exceed expectations. The deeper you look into the universe, the more it resembles a recurring lesson in humility. Every time astronomers believe they have approached a reasonable estimate, nature quietly reveals that the true number is larger. The Hubble deep fields have already shown that seemingly empty regions of space are crowded with galaxies. Yet the full significance of those observations takes years to unfold. Researchers continue analyzing data, refining models, and asking a difficult question: what if most galaxies are simply too faint for us to see? You can picture the challenge. Suppose you stand on a hill overlooking a vast city at night. Bright skyscrapers are easy to count. Streetlights are visible. Major buildings stand out clearly. But what about small houses hidden in darkness? What about distant neighborhoods beyond the horizon? Your count would capture the obvious structures while missing countless others. Astronomers face a similar problem. The galaxies easiest to detect are generally the brightest and largest. Smaller galaxies, especially ancient ones in the distant universe, can evade observation as data accumulates. Scientists begin constructing more sophisticated models of galaxy evolution. They estimate how galaxies grow through mergers. They examine how many small galaxies likely existed in the early universe. They compare observations with simulations. The results become increasingly surprising. A mainstream historical fact arrives in 2016 when a team of researchers publishes an analysis suggesting that the observable universe may contain around 2 trillion galaxies, far more than the commonly cited estimate of roughly 100 billion. 2 trillion, the number is so large that it almost resists comprehension. Written numerically, it appears as 2 mil thousand thousand. Your eyes naturally slide across the zeros and lose interest halfway through. Human intuition was not designed for trillions. It struggles enough with grocery receipts. Yet the research indicates that the majority of galaxies may be too faint or distant for current telescopes to detect directly. In other words, the visible galaxy population could represent only a small fraction of the total. The universe may contain an enormous hidden population of faint galaxies scattered throughout cosmic history. The revelation feels familiar. Once, humanity believed the Milky Way was the universe. Then astronomers discovered billions of galaxies. Now, evidence suggests there may be trillions. The pattern continues. Every larger answer eventually becomes a smaller one. A quirky tidbit emerges from public reactions to these estimates. Many people initially assume that 2 trillion galaxies means astronomers have literally counted everyone. Not quite. Nobody sits at a computer clicking Galaxy 1, Galaxy 2, Galaxy 3, and so on until retirement. The estimate comes from statistical analysis, observations, and modeling. Fortunately for astronomers, because counting 2 trillion objects manually would be a slightly ambitious weekend project. The new estimate generates excitement but also caution. Science rarely treats a single number as sacred. Researchers examine assumptions, test methods, compare independent analyses, debate uncertainties. Historians still argue whether future observations will validate the higher estimates fully or require significant revision. The exact number remains an active area of investigation, and that uncertainty is important. Astronomy is not claiming absolute certainty about 2 trillion galaxies. Rather, it is presenting the best estimate based on available evidence. The true number could differ, perhaps somewhat lower, perhaps somewhat higher. The universe has surprised us before. It may do so again. As you drift through these enormous figures, another realization emerges: not all galaxies are equal. When people imagine galaxies, they often picture majestic spirals like the Milky Way or Andromeda. Those galaxies are spectacular. They are also relatively uncommon compared with smaller dwarf galaxies. Dwarf galaxies contain fewer stars and often orbit larger galaxies. Many are faint. Some are extremely difficult to detect. Yet they may account for a substantial fraction of the galactic population. Imagine counting animals in a forest while overlooking most of the insects. your estimate would be incomplete. Similarly, missing large numbers of dwarf galaxies could dramatically affect the total count. Researchers therefore devote increasing attention to these small systems. Tiny galaxies become unexpectedly important. A galaxy containing a few million stars may seem insignificant compared with one containing hundreds of billions. But when trillions of galaxies are involved, even small members matter. The census depends on them. You begin to appreciate the scale of the challenge. Astronomers are not merely counting galaxies. They are estimating populations across space and time. They must account for visible galaxies, hidden galaxies, ancient galaxies, merged galaxies, and galaxies that may never be observable directly. The task resembles reconstructing the history of an entire forest from a handful of leaves. And yet remarkable progress continues. Computers process enormous datasets. Observatories survey millions of objects. Space telescopes peer deeper into the cosmos than previous generations considered possible. Each advance sharpens the picture. Still, no matter how impressive the numbers become, they carry a deeper implication. If the observable universe contains around 2 trillion galaxies, and each galaxy contains millions or billions of stars, then the total number of stars becomes almost unimaginably vast. The night sky visible from Earth suddenly represents a tiny sample of reality, a tiny sample of a tiny sample. The universe grows larger with every calculation, and even now, hidden populations may remain beyond reach. Some galaxies are so faint that they blend into darkness itself. Others may exist near the limits of observation, waiting for future telescopes to reveal them. The cosmic census remains unfinished, the count continues. And before long, you will encounter galaxies so small, strange, and unusual that they challenge the very idea of what a galaxy is supposed to be. By now, the universe contains far more galaxies than anyone once imagined. Billions became hundreds of billions. Hundreds of billions may have become trillions, yet an equally fascinating question begins to emerge from the cosmic census. What exactly counts as a galaxy? At first, the answer seems obvious. A galaxy is a large collection of stars bound together by gravity, sibled, comforting, neatly organized. The universe, however, has little interest in staying neatly organized. As astronomers discover more objects, they encounter systems that blur categories and challenge assumptions. Some galaxies are gigantic. Others are tiny. Some display elegant spiral arms. Others resemble scattered clouds of stars with no obvious structure. The cosmic filing cabinet becomes increasingly messy. A mainstream historical fact comes from the work of astronomers throughout the 20th century who developed galaxy classification systems, most famously the tuning fork diagram introduced by Edwin Hubble. This scheme grouped galaxies into spirals, ellipticals, and other broad categories, providing a framework still used today. The classification proved enormously useful. But nature immediately began producing exceptions. As usual, you can imagine a teacher creating a perfectly organized seating chart only to discover that the students have collectively decided to ignore it. The universe behaves similarly. Some galaxies fit beautifully into standard categories. Others seem determined to cause paperwork problems. Consider dwarf galaxies. These small systems contain far fewer stars than giants like the Milky Way. While the Milky Way contains hundreds of billions of stars, some dwarf galaxies possess only a few million. That is still an impressive number, of course. A few million stars would dominate any neighborhood. Yet, compared with a giant spiral galaxy, a dwarf galaxy can seem almost modest. The surprising part is how common they may be. Many astronomers suspect dwarf galaxies vastly outnumber large galaxies. Think of trees in a forest. Towering giants attract attention, but smaller plants often account for much of the population. The same may be true among galaxies. And dwarf galaxies are not merely miniature versions of larger systems. Some have unusual histories. Some appear distorted by gravitational interactions. Others orbit larger galaxies, like loyal companions. A quirky tidbit involves one of the faintest known satellite galaxies surrounding the Milky Way. Certain dwarf galaxies are so dim that astronomers detect only a small number of visible stars. Entire galaxies can remain hidden for ages because they are barely brighter than the surrounding darkness. Imagine misplacing an entire galaxy. The universe apparently considers that acceptable. As observations improve, astronomers discover increasingly strange objects. Some galaxies possess long tidal tails stretching across enormous distances. Others appear warped. Some are actively colliding. Others are being torn apart by gravity. You begin to realize that galaxies are not static monuments. They are dynamic systems. They grow, interact, sometimes dramatically. When galaxies collide, the process unfolds over millions or billions of years. Stars generally pass by one another without direct collisions because the distances separating them are immense. If stars were grains of sand, the spaces between them would still be enormous. Galaxies look crowded from afar. Up close, they are mostly emptiness. That remains one of astronomy's favorite surprises. Historians still argue whether current definitions of galaxies adequately describe all observed systems or whether future classifications will require significant revisions. As more unusual objects are discovered, the boundaries become less clear. Some researchers even debate certain borderline objects that occupy the gray area between star clusters and galaxies. Where exactly does one category end and another begin? Nature offers no labels, only observations, and observations often resist simplicity. Meanwhile, giant galaxies continue attracting attention. Among the largest known galaxies are enormous elliptical systems containing trillions of stars. These cosmic giants often occupy the centers of galaxy clusters and dominate their surroundings through sheer gravitational influence. Standing beside one would be impossible, of course. But if you could somehow compare it with the Milky Way, the difference would be staggering. It would feel like comparing a city to a continent. Yet even these giants represent only part of the story. Astronomers increasingly recognize that understanding galaxy populations requires studying every size scale. Large galaxies, small galaxies, bright galaxies, faint galaxies, regular galaxies. Bizarre galaxies, the universe does not favor uniformity, it favors diversity. You drift through a cosmic menagerie filled with spirals, ellipticals, dwarfs, irregulars, ring galaxies, interacting galaxies, and systems so peculiar that researchers occasionally describe them with phrases that sound suspiciously like scientific shrugs. Translation: we found something strange. This diversity matters because galaxy counts depend on what qualifies as a galaxy. A universe filled primarily with giant spirals would contain far fewer galaxies than a universe crowded with tiny dwarf systems. And evidence increasingly points toward the latter. Many galaxies may be small, faint, and difficult to detect. They contribute little light individually. Together, however, they may represent a significant fraction of the total population. The census, therefore, becomes more complicated than simply counting visible spirals. Astronomers must estimate hidden populations, classify unusual systems, and understand how galaxies evolve over time. Every new discovery adds richness to the picture, but it also introduces fresh uncertainty. The more carefully humanity studies galaxies, the more diverse they appear. And beyond that diversity lies another challenge entirely. Some galaxies are not merely small or strange, some are almost invisible. They lurk in darkness, emitting so little light that detecting them becomes extraordinarily difficult. If enough of these hidden systems exist, then even the astonishing estimates discussed so far may still be incomplete. The cosmic census may be missing entire populations waiting in the shadows. And the next step in your journey leads directly into that darkness. The deeper your exploration goes, the more you discover that the universe is remarkably good at hiding things. Not because it is trying to be mysterious, not because galaxies enjoy practical jokes, simply because distance, darkness, and the limits of observation create countless opportunities for objects to escape notice. By now, you have encountered giant galaxies, dwarf galaxies, spiral galaxies, and irregular galaxies. You have watched galaxy estimates rise from billions to trillions. Yet there remains an uncomfortable possibility. What if many galaxies are still missing from the count? What if entire populations exist beyond the reach of current instruments? This question becomes increasingly important as astronomers study the faintest structures in the cosmos. A mainstream historical fact emerges from late 20th and early 21st century surveys that reveal numerous ultra-faint dwarf galaxies surrounding the Milky Way. These discoveries dramatically increase awareness that many galaxies are so dim they can remain undetected for long periods. Some of these systems contain surprisingly few visible stars. From a distance, they are almost ghosts. Tiny collections of ancient stars drifting through space, barely distinguishable from the darkness around them. Finding them is extraordinarily difficult. Imagine standing on a mountaintop at midnight and trying to identify a single candle placed hundreds of kilometers away. Now imagine that the candle occasionally hides behind fog. That is closer to the challenge astronomers face. The universe contains objects that simply do not produce much light, and astronomy, despite all its sophistication, still depends heavily on light. A quirky tidbit from modern observations is that researchers occasionally discover previously unknown dwarf galaxies in data that has already been examined multiple times. The galaxies were there all along, quietly blending into the background until improved analysis techniques finally revealed them. Some cosmic discoveries amount to finding a galaxy in the scientific equivalent of a cluttered drawer. How long has that been there? Apparently, quite a while. The existence of these faint galaxies raises a profound question: how many more remain hidden? If astronomers continue discovering ultra-faint systems close to the Milky Way, then similar objects may exist throughout the observable universe, potentially in enormous numbers. And because dwarf galaxies likely outnumber giant galaxies, missing even a fraction of them could significantly affect population estimates. You begin to appreciate why galaxy counting remains such a difficult problem. It is not enough to count visible objects. Astronomers must estimate invisible populations as well. This requires careful statistical modeling, simulations, and indirect evidence. Researchers ask questions like, how many galaxies should exist according to theoretical models? How many are actually observed? What percentage might be hidden below current detection thresholds? The answers are rarely simple. Historians still argue whether future observations will uncover enough faint galaxies to substantially alter present estimates or merely refine them. The debate remains active because technology continues improving. Every new telescope expands the search, and every expansion introduces surprises. Some hidden galaxies may contain very few stars but substantial amounts of dark matter. Others may have experienced little star formation for billions of years. Some appear as relics from the early universe, surviving almost unchanged across immense spans of cosmic history. These galaxies are valuable, not because they are large, not because they are bright, but because they preserve information about how galaxies formed long ago. In a sense, they function as archaeological sites, cosmic fossils scattered through space. You can almost imagine astronomers gently brushing dust from ancient ruins. Except the ruins are galaxies, and the excavation tools cost hundreds of millions of dollars. Astronomy occasionally has expensive hobbies. As researchers search for hidden galaxies, they also confront another challenge: distance. The farther away a galaxy lies, the fainter it becomes. At extreme distances, even large galaxies can fade below detection limits. Light spreads out, brightness decreases, observation becomes increasingly difficult. This means that many ancient galaxies from the early universe may remain invisible to current instruments. Not because they are rare, because they are faint, the distinction matters. A galaxy can exist without being observable, and the observable universe contains only what light has managed to deliver to us. You drift deeper into this realization. The cosmic census resembles an iceberg more than a complete inventory. Visible galaxies form the portion we can study directly. Below that surface may lie substantial hidden populations. Some are concealed by faintness, others by distance, others by limitations in current technology. Astronomers therefore develop increasingly sophisticated techniques. Computer simulations model galaxy formation across billions of years. Large surveys search systematically for faint structures. Machine learning algorithms help identify subtle patterns in enormous datasets. The search becomes more powerful every year, yet uncertainty remains. And uncertainty can be exciting. After all, if every galaxy had already been counted, much of the adventure would be over. Instead, the universe continues offering mysteries. You also begin noticing another recurring theme. Whenever astronomers encounter missing galaxies, another invisible ingredient often appears in the discussion. Dark matter. Again and again, evidence suggests that galaxies are influenced by something unseen, something that exerts gravity but emits no detectable light. Something that may determine where galaxies form and how they evolve. The hidden galaxies lead naturally toward the hidden structure beneath them. Because visible matter alone cannot explain everything astronomers observe, the stars are only part of the story. The gas is only part of the story. The galaxies themselves may rest upon an enormous invisible framework stretching throughout the cosmos. And understanding that framework may prove essential for understanding how trillions of galaxies came to exist in the first place. The next stage of your journey takes you beyond visible light and into one of the greatest mysteries in modern science. A mystery that may hold the key to the universe's vast population of galaxies. A mystery known as dark matter. By this point in your journey, galaxies seem to be everywhere. Large galaxies, tiny galaxies, bright galaxies, ghostly galaxies hiding at the limits of detection. And yet an even stranger realization now begins to emerge. The stars you see may not be the main story. In fact, most of the matter responsible for shaping galaxies may be completely invisible. You settle into this idea carefully, because it sounds like the opening line of a science fiction novel. Yet it arises from decades of observation. Astronomers repeatedly discover that visible matter alone cannot explain what galaxies actually do. A mainstream historical fact comes from the work of Fritz Zwicky in the 1930s. While studying galaxy clusters, Zwicky found evidence that much more mass existed than could be accounted for by visible stars and gas. The galaxies were moving too rapidly to be held together by the matter astronomers could see. Something appeared to be missing. Or rather, something appeared to be present but invisible. At the time, many scientists remained skeptical. Extraordinary claims require strong evidence, and evidence takes time to accumulate. Over the following decades, more clues emerged. Perhaps the most famous involved galaxy rotation, when astronomers measured how quickly stars orbit around galactic centers. They encountered a puzzle. According to ordinary expectations, stars far from the center should move more slowly. That is roughly how planets behave in the solar system. The outer planets orbit more slowly than the inner ones. Galaxies, however, refuse to cooperate. Stars far from galactic centers often moved much faster than expected. The visible matter simply was not sufficient to explain the observed motion. The numbers did not add up. And mathematics, unlike people, tends to be very stubborn about such things. A major figure in this story is Vera Rubin, whose observations helped establish the reality of the problem. Her work provided some of the strongest evidence that galaxies contain enormous amounts of unseen mass. Today, that unseen component is known as dark matter. The name sounds dramatic. In truth, it merely means matter that does not interact with light in ways we can directly observe. Dark matter does not appear dark because it is black. It appears dark because it is effectively invisible. If you could somehow look at a galaxy through magical eyes capable of seeing dark matter, the galaxy would appear vastly larger than the visible stars suggest. The glowing spiral would sit inside an enormous halo of unseen material, and this invisible halo plays a crucial role. A quirky tidbit often surprises people when they first learn about dark matter. According to current estimates, the stars, planets, gas, dust, and everything familiar make up only a small fraction of the universe's total matter content. The luminous parts, the beautiful things appearing in telescope photographs, may be only the decorative frosting on a much larger cosmic cake. The universe appears to be mostly composed of ingredients humanity cannot directly see. A slightly humbling recipe. As astronomers investigate galaxy formation, dark matter becomes increasingly important. Computer simulations reveal something remarkable. Without dark matter, galaxies struggle to form in ways that resemble the observed universe. With dark matter included, the results improve dramatically. The invisible matter acts like scaffolding. Visible matter falls into dark matter structures under gravity. Stars form, galaxies emerge, clusters develop. Over billions of years, a vast cosmic web takes shape. You begin picturing the universe differently, not as isolated islands floating randomly through space. Instead, imagine countless galaxies connected by an enormous invisible framework stretching across unimaginable distances. The galaxies mark the brightest intersections. The underlying structure remains hidden, yet its gravitational influence shapes everything. Historians still argue whether future discoveries will reveal dark matter to be a new particle, a collection of particles, or evidence that some aspect of gravity itself remains misunderstood. Despite decades of study, the exact nature of dark matter remains unresolved. That uncertainty keeps the mystery alive. Scientists know something is happening. The challenge is determining exactly what. Meanwhile, observations continue accumulating. Galaxy clusters reveal dark matter through gravitational effects. Light from distant objects bends as it passes massive structures, creating phenomena known as gravitational lenses. These lenses allow astronomers to map invisible mass indirectly. The results repeatedly point toward large quantities of unseen matter. You cannot see it, but you can see what it does, rather like noticing footprints in fresh snow without seeing the animal that left them. And the footprints are everywhere. Dark matter also helps explain why galaxy populations become so enormous. In the early universe, tiny variations in matter density gradually grow under gravity. Dark matter halos attract additional material. Small galaxies form first. Larger galaxies emerge through mergers and growth. Over billions of years, the universe constructs a vast hierarchy of structures. The result is the galaxy-rich cosmos observed today. Without that invisible framework, the story becomes much harder to explain. You drift through simulations showing filaments of matter stretching across hundreds of millions of light years. At the intersections sit clusters of galaxies, thousands of galaxies, sometimes tens of thousands, each cluster functioning as a massive city within the larger cosmic web, the scale becomes astonishing. Not only are there perhaps trillions of galaxies, but those galaxies themselves appear organized within structures shaped by invisible matter. The universe is simultaneously larger and stranger than previous generations imagined. And the story is still unfolding, because understanding dark matter helps explain how galaxies form. But to understand how many galaxies exist, you must travel even farther back toward the earliest epochs of cosmic history. Back toward the time when the first galaxies emerged from darkness. Only by exploring those ancient beginnings can you understand how the universe became populated with so many islands of light. And soon, you will witness the birth of galaxies themselves. The invisible scaffolding of dark matter now stretches across your imagination like a vast cosmic framework. Upon that framework, galaxies emerge. They grow, they merge, they evolve. But to understand why the observable universe may contain trillions of galaxies, you must travel backward through time, far backward, past the Milky Way, past Andromeda, past galaxy clusters and superclusters, back toward the earliest chapters of cosmic history. You are not moving physically, you are moving through light, because every telescope functions partly as a time machine. The farther astronomers look, the older the light becomes. A galaxy observed 10 billion light-years away appears roughly as it existed 10 billion years ago. Its ancient photons have spent eons crossing space before finally reaching Earth. By collecting this ancient light, astronomers reconstruct the universe's history. A mainstream historical fact comes from the discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson. This faint glow provides a snapshot of the young universe and offers crucial evidence for the Big Bang model. At that early stage, galaxies do not yet exist. Stars do not yet exist. Planets certainly do not exist. The universe is hot, dense, and remarkably uniform. Not perfectly uniform, just slightly uneven, and those tiny imperfections change everything. You can imagine a perfectly calm pond. Drop a pebble into it, and patterns begin to emerge. The early universe contains small variations in density. Some regions possess slightly more matter than others. Gravity gradually amplifies those differences. Over millions of years, matter accumulates, clouds form, structures develop, the first galaxies begin taking shape. It is an astonishing process. The entire population of galaxies ultimately traces its origins to tiny fluctuations present shortly after the universe began. Cosmic architecture emerging from microscopic irregularities. A quirky tidbit often surprises people here. If the early universe had been perfectly smooth, galaxies might never have formed at all. No galaxies, no stars, no planets, no astronomy videos. The existence of every galaxy depends upon tiny imperfections. Sometimes the universe demonstrates that flaws can be remarkably productive. As time passes, the first stars ignite. These stars differ from many stars you see today. They form in an environment containing almost no heavy elements. The early universe consists primarily of hydrogen and helium, the heavier elements familiar to modern life. Carbon, oxygen, iron, calcium, and countless others must be manufactured inside stars. The first generations of stars therefore help transform the universe chemically. They become cosmic factories. When massive stars die, they enrich surrounding space with newly forged elements. Future generations of stars inherit those materials. Galaxies grow increasingly complex. You drift through hundreds of millions of years. Small galaxies emerge first. This detail turns out to be important. Many modern theories suggest that galaxy formation proceeds from the bottom upward. Tiny systems form early. Larger systems arise later through mergers and growth. Countless small galaxies combine to create larger structures. Imagine villages merging into towns, towns merging into cities, cities merging into sprawling metropolitan regions. The universe follows a somewhat similar pattern. Galaxies are builders as well as buildings. Historians still argue whether current models fully capture the details of early galaxy formation or whether important processes remain poorly understood. New observations frequently challenge assumptions about how quickly the first galaxies appeared. That uncertainty reflects a broader truth. The early universe remains one of astronomy's most active research frontiers. Researchers continue discovering galaxies that appear surprisingly mature for their age. Some seem larger, brighter, or more evolved than expected. The cosmos occasionally behaves like a student completing assignments before the official deadline. Astronomers notice, as the first galaxies multiply, gravitational attraction encourages them to gather into larger structures. Clusters begin forming, filaments emerge, the cosmic web becomes increasingly pronounced. Over billions of years, the universe develops the large-scale architecture visible today, and throughout this process, galaxy numbers increase dramatically. Tiny galaxies form, some merge, others survive independently. Many continue evolving across cosmic time. The result is a universe rich with diversity and complexity. You begin appreciating why counting galaxies involves more than a single number. The galaxy population changes throughout history. At certain times, many more small galaxies may have existed than survive today. Mergers gradually reduce the total count while simultaneously creating larger systems. A galaxy census therefore depends on when in cosmic history you perform the count. The universe is not a static museum. It is an evolving ecosystem. That realization becomes especially important as astronomers search for ancient galaxies. Every newly discovered early galaxy provides another clue about how the population developed. Every observation helps refine estimates. And increasingly powerful telescopes continue pushing deeper into cosmic history. The goal is ambitious. Researchers want to observe some of the earliest galaxies ever formed. They want to witness the dawn of cosmic structure itself, and humanity now possesses instruments capable of doing exactly that. A new generation of telescopes is opening windows into the ancient universe. Through those windows, astronomers are discovering galaxies from epochs once considered unreachable. The view is transforming ideas about galaxy evolution. It may even reshape estimates of how many galaxies exist, because the farther back you look, the more surprises the universe seems determined to provide. The farther back you travel through cosmic history, the stranger the universe becomes. For generations, astronomers dreamed of observing the earliest galaxies. They wanted to see the first great structures emerge from the darkness that followed the Big Bang. They wanted to understand how quickly galaxies formed and how rapidly the universe filled with light. For a long time, those goals seemed almost unreachable. Distant was the enemy. The earliest galaxies are unimaginably far away. Their light is faint. Much of it has been stretched by cosmic expansion into longer wavelengths. Detecting such ancient objects requires extraordinary instruments. Eventually, those instruments arrive. A mainstream historical fact unfolds with the launch of the James Webb Space Telescope. Designed to observe the universe in infrared light, Webb allows astronomers to peer deeper into cosmic history than previous space telescopes could manage. The scientific community waits eagerly. Expectations are high. The universe responds by immediately creating fresh puzzles. As Webb begins sending back observations, researchers discover galaxies that appear surprisingly bright, surprisingly massive, or surprisingly mature for their age. Some of these galaxies seem to have formed earlier than many models predicted. Not impossibly early, just early enough to make astronomers raise their eyebrows. And in science, raised eyebrows are often the beginning of interesting discoveries. You can almost picture researchers examining fresh data while quietly muttering, "Well, that's unexpected." The universe has heard those words many times. A quirky tidbit about modern astronomy is that new telescope observations occasionally generate headlines suggesting that everything scientists know has been overturned. Usually, reality is less dramatic. Most discoveries refine existing understanding rather than destroy it. Still, the excitement is genuine. Each new observation provides another glimpse into the universe's youth, and those glimpses are astonishing. Webb reveals galaxies from periods when the cosmos was only a small fraction of its current age. You are looking back more than 13 billion years. The light reaching the telescope began its journey long before Earth existed in its present form, long before the Sun formed, long before the Milky Way resembled the galaxy you know today. The scale of time becomes almost dreamlike. You watch ancient galaxies shining across epochs that seem impossible to visualize. Some appear compact, others exhibit complex structures. Many are actively forming stars at tremendous rates. The early universe appears energetic and dynamic, not empty, not simple, alive with activity. Historians still argue whether some early Webb observations indicate genuinely unexpected galaxy growth rates, or whether existing theories can accommodate the findings with modest adjustments. The debate remains active because the data are still being analyzed and interpreted. That ongoing discussion is exactly what makes astronomy exciting. Each answer creates new questions. Every observation opens additional doors. The story continues expanding. Meanwhile, Webb's discoveries contribute directly to the galaxy counting problem. Remember the hidden populations discussed earlier. The faint galaxies, the distant galaxies, the systems too ancient or too dim for earlier telescopes to detect. Webb helps uncover portions of that hidden population. It allows astronomers to observe objects that previously existed only as theoretical possibilities. Suddenly, some of the missing pieces begin appearing. Not all of them, but enough to improve estimates, enough to refine models, enough to remind humanity that the cosmic census remains unfinished. You begin to appreciate how galaxy counting evolves alongside technology. The universe itself does not change dramatically over a few decades. Human vision changes, human instruments improve, human reach extends farther. Each technological leap reveals additional layers of reality. The pattern has repeated throughout the history of astronomy. Galileo sees stars within the Milky Way. Hubble proves other galaxies exist. Deep field observations uncover thousands of distant galaxies. Webb explores the earliest eras of galaxy formation. Every generation inherits a larger universe than the one before. There is something quietly beautiful about that progression. Knowledge expands. Wonder expands with it. You drift through images filled with ancient galaxies glowing red in infrared light. Some of these objects represent the ancestors of modern galaxies. Others may have merged long ago into larger systems. Many no longer exist in the forms observed today. The universe is constantly changing. Galaxies are born, they evolve, they collide, they transform. They sometimes disappear into larger structures. The cosmic census therefore resembles a family tree as much as a population count. Each galaxy possesses a history. Each contributes to the broader story, and that story remains incomplete. Future observatories will continue exploring deeper distances. More powerful instruments will detect fainter objects. Additional surveys will map larger regions of the sky. Every advancement promises fresh discoveries. Perhaps new populations of galaxies await detection. Perhaps hidden structures remain unseen. Perhaps future estimates will once again exceed current expectations. The possibility remains open, and that uncertainty leads naturally toward a profound question. Even with the most advanced telescopes humanity can build, Will it ever be possible to count every galaxy? Or are there limits beyond which observation cannot go? The answer lies not merely in technology, but in the nature of the observable universe itself. Soon you will reach the edge of what can, in principle, be seen. And there you will confront one of the deepest questions in all of cosmology. As your journey approaches the edge of the observable universe, the question becomes increasingly philosophical as well as scientific. How many galaxies exist? At first, it seems like a straightforward counting problem. Don't find galaxies, add them together. Write down the answer, yet every step of your exploration has revealed complications. Galaxies evolve, galaxies merge, many galaxies remain faint. Some are difficult to classify. Others hide beyond current detection limits. And now you encounter perhaps the greatest challenge of all. The observable universe is not necessarily the entire universe. That distinction changes everything. A mainstream historical fact emerges from 20th century cosmology. As scientists developed modern models of cosmic expansion, they recognized that light travels at a finite speed and that the universe has a finite age. Consequently, there is a limit to how far we can observe. This limit is called the observable universe. It contains everything whose light has had enough time to reach us since the beginning of cosmic expansion. Beyond that horizon may lie additional galaxies, perhaps countless additional galaxies. But their light has not reached Earth, at least not yet. You can imagine standing in a vast forest at night carrying a lantern. The lantern illuminates a certain region. You can study everything inside that circle of light. Outside it, the forest continues, but you cannot directly observe it. The observable universe functions in a somewhat similar way. Humanity's cosmic lantern is limited by time itself. No telescope can collect light that has not arrived. No technology can simply bypass that restriction. The universe imposes a fundamental observational boundary. And that means the galaxy counts discussed so far apply specifically to the observable universe, perhaps around 2 trillion galaxies, perhaps somewhat more, perhaps somewhat less. The exact figure remains under investigation. But regardless of the final number, it refers only to the portion of reality accessible to observation. The larger universe may extend far beyond. A quirky tidbit often surprises people here. The observable universe has a radius of roughly 46 billion light-years, even though the universe is approximately 8 billion years old. At first glance, that sounds impossible. How can you observe something farther away than light could have traveled? The answer involves cosmic expansion. Space itself has been stretching while the light travels, increasing distances over time. The universe enjoys presenting geometry problems that make ordinary intuition quietly leave the room. As cosmologists explore these ideas, fascinating possibilities emerge. Maybe the entire universe is much larger than the observable portion, perhaps vastly larger. Some models even suggest that the universe could be effectively infinite. If so, the number of galaxies might also be enormous beyond comprehension, possibly infinite as well. That word deserves careful handling. Infinite is not simply a bigger version of a trillion. It is a fundamentally different concept. Human brains struggle with it, quite reasonably. Most of our daily experiences involve manageable quantities, traffic jams, coffee cups, laundry piles, not infinite collections of galaxies. Historians still argue whether certain cosmological models provide the best description of the universe's global structure. Questions about the overall size and geometry of the cosmos remain active areas of research. This uncertainty matters. Astronomers can estimate galaxies within the observable universe because observations provide data. Beyond the observable horizon, evidence becomes indirect. Theoretical models guide understanding. Observations constrain possibilities, but complete certainty remains elusive. You drift through this realization. For centuries, people imagined reaching the edge of the world. Then the edge moved farther away. Later, humanity imagined reaching the edge of the solar system, then the galaxy, then the observable universe. Each time, the horizon shifted, knowledge expanded. Mystery expanded alongside it. There is something wonderfully consistent about that pattern. The universe remains larger than current understanding. Not because science is failing, because discovery is ongoing. Every generation inherits unanswered questions. Every generation contributes new answers. And every answer reveals additional mysteries. The galaxy counting problem captures that process beautifully. The original estimate might have been one galaxy, the Milky Way alone. Then came millions, then billions, then hundreds of billions, then trillions. Future revisions remain entirely possible. New telescopes may reveal additional populations. Better models may refine existing estimates. Improved surveys may uncover faint galaxies previously overlooked. The census continues. Yet there is another perspective worth considering. Perhaps the most important lesson is not the exact number itself. Perhaps it is what the search reveals about humanity. You are a species living on a small planet orbiting an ordinary star within one galaxy among trillions. And yet you have learned to measure distances across billions of light years. You have discovered galaxies invisible to the naked eye. You have reconstructed cosmic history stretching back almost to the beginning. You have transformed curiosity into understanding. That achievement is extraordinary. The galaxies themselves are magnificent. The fact that conscious beings can study them may be equally remarkable. As you approach the final stage of your journey, your attention turns beyond the observable horizon itself, toward galaxies whose light may never reach us, toward regions forever hidden, toward questions that perhaps cannot be answered completely. There, at the boundary between knowledge and mystery, the universe offers one final reflection on what it means to count galaxies at all. You have traveled from ancient ideas about the Milky Way to the deepest observations of modern astronomy. You have watched the universe grow larger again and again. First there was one galaxy, then many galaxies, then billions, then perhaps trillions. And now, as you drift toward the quiet edge of the observable universe, the question that began this journey returns one final time. How many galaxies exist in the universe? The most honest answer is both satisfying and wonderfully incomplete. Within the observable universe, current research suggests there may be on the order of trillions of galaxies when faint and distant populations are taken into account. Not merely a few billion, not merely hundreds of billions, potentially trillions, yet beyond the observable horizon, nobody knows for certain. The universe may extend vastly farther, perhaps unimaginably farther, perhaps infinitely farther. And if galaxies continue beyond the observable boundary, then the true total could be far greater than any number humanity can currently estimate. A mainstream historical fact worth remembering is that every major expansion in humanity's cosmic understanding has pushed us away from the center. The Earth was not the center of the solar system. The Sun was not the center of the galaxy. The Milky Way was not the center of the universe. Again and again, the cosmos has revealed itself to be larger than expected. Yet this lesson is not depressing. Quite the opposite. It means there is always more to discover. The universe remains generous with mysteries. A quirky tidbit captures that spirit perfectly. If every galaxy in the observable universe were reduced to the size of a grain of sand, the collection would still create an immense landscape stretching beyond comfortable imagination. Even when transformed into tiny symbols, galaxies refuse to become small. Scale follows you everywhere in astronomy, and scale has been the secret companion of this entire journey. You began beneath a night sky filled with stars. Now you understand that many of those stars belong to one galaxy among an astonishing multitude. You understand that galaxies gather into clusters. Clusters connect through filaments. Invisible dark matter helps shape cosmic structure. Ancient galaxies illuminate the early universe. Modern telescopes continue uncovering hidden populations. The story is far richer than a simple number. Historians still argue whether future generations will look back on today's estimates as remarkably accurate or charmingly incomplete. The debate remains open because the universe continues offering new data. Perhaps future telescopes will reveal additional faint galaxies. Perhaps entirely new observational techniques will emerge. Perhaps some assumptions underlying present estimates will require revision. Science welcomes such possibilities. Knowledge grows through correction. The cosmic census remains a work in progress. And that may be exactly as it should be. After all, if every mystery vanished tomorrow, the universe would become a far quieter place. Instead, the darkness beyond our current understanding continues inviting exploration. You can almost picture those distant galaxies now. Some shine brightly. Some glow faintly. Some formed shortly after the universe itself began. Others continue evolving today. Many will never be visited. Most will never even be seen directly by human eyes. Yet they exist nonetheless, scattered across the cosmos like islands of light in an immeasurable sea, and somewhere among them lies the Milky Way. Within the Milky Way lies the solar system. Within the solar system lies Earth. Upon Earth, a curious species looks upward and asks questions. That chain of perspective is astonishing, not because humanity occupies a central position, because humanity can understand any of it at all. The universe does not appear designed to be easily comprehended. Its scales are enormous. Its history spans billions of years. Its structures stretch across distances that challenge imagination. Yet little by little, observation by observation, generation by generation, understanding grows. And now, as the journey finally begins to slow, the numbers themselves become less important than the feeling they inspire. A feeling of vastness, a feeling of wonder, a feeling that reality extends far beyond ordinary experience. The galaxies remain out there, turning slowly through the darkness. Some are ancient, some are young. Some may shine long after every human story has faded into history. They drift through space without concern for calendars, civilizations, or questions, yet their light reaches us. And through that light, we learn. Through that light, we measure. Through that light, we dream. The answer to how many galaxies exist may never be final. But perhaps that is fitting. A universe that can be fully counted might feel smaller. A universe that always contains another horizon, another mystery, another possibility. That is a universe worthy of wonder. And with that thought, you allow the immense cosmic landscape to settle gently around you. The galaxies continue their silent dance. The stars continue shining. The darkness remains vast, but no longer empty. You simply float among the ideas, unhurried and calm, carried by the knowledge that existence is larger than any map humanity has yet drawn. For tonight, that is enough. As your thoughts become slower and softer, the universe seems less like a puzzle demanding answers, and more like an ocean inviting quiet contemplation. The countless galaxies remain where they have always been, scattered across the depths of space, glowing patiently in the dark. And now, it is time to drift peacefully through that darkness. The night sky above you grows still. Not truly still, of course. Galaxies continue spinning. Stars continue burning. Space itself continues expanding. Yet in your imagination, everything softens into a gentle rhythm. You no longer need to count anything. No estimates, no equations. No catalogues stretching across billions of light years. Only the quiet awareness that beyond every visible star lies a universe rich with structure, history, and possibility. The Milky Way drifts silently among countless companions. Galaxy clusters float through immense cosmic webs. Ancient light crosses the darkness, traveling patiently across billions of years before reaching distant worlds. The scale is enormous, yet somehow comforting. The galaxies ask nothing from you. They require no solutions tonight. They simply exist. You can let the numbers fade now, let the debates fade, let the measurements fade. Keep only the feeling of wonder. Imagine yourself resting beneath a sky so clear that the Milky Way stretches from horizon to horizon, a pale river of starlight flowing through the darkness. Beyond it lie other galaxies. Beyond those lie more galaxies still, and beyond them, perhaps horizons no observer will ever reach. Yet there is peace in not knowing everything. There is beauty in mystery. There is comfort in realizing that the universe remains vast enough to surprise every generation that studies it. The darkness grows quieter. The stars seem softer. The distant galaxies become gentle points of light scattered across an endless cosmic sea. You float among them for a moment longer, calm and unhurried, carried by the steady current of imagination. And as the universe slowly fades into the background of thought, sleep can arrive just as gently, like starlight crossing space, patient, silent and serene. End of script. Sweet dreams.